Okay, thank you so much, Franco, for this invitation, and then for all of you for being here. Although I understand this is a class and you're required to be here. So what class is this?
It's a seminar series.
Seminar series. So are you all civil engineering students?
Yes.
I see. Okay. So this talk will be, so from my understanding of this seminar series, you're all looking to explore some aspects of machine learning as applied to different engineering disciplines, among other things, right? And this is very much going to be in those lines. It is sort of a theoretical area called generalization, which tries to study how well a learned system performs on data that is not used for training. So I'm going to just assume a background in some familiarity rather with working with neural networks. Is that fair for the audience? Yeah. So you've all trained neural networks, worked with them, and or maybe at least heard of them, right? Like used them in your research, maybe. And the point of this talk is to show you some kind of intersections between this area of dynamical systems, which some of you may have studied if you have an engineering background. Maybe you've taken some controls, nonlinear dynamics, dynamics classes. Some of you are from a physics background, so I assume you have definitely seen it somewhere. The promised pizza has also arrived. So feel free if you want to grab it. I wouldn't be offended. So with this in mind, let's try to understand some intersections or problems at the intersection of dynamical systems and this broad area of statistical machine learning. Statistical machine learning deals with several questions, central to which is how well can you learn a model if you have some kind of observations or data about the model. And mainly the question it tries to study rigorously is if you have a finite amount of data, and as you keep increasing the amount of data you have, intuitively you will learn better and better, right? And the central object of statistical learning is to quantify how well this happens. What is the rate at which if you increase the data, your error in the learned model decreases. Now, what does this have to do with dynamical systems, which is the other area that we are going to connect to statistical learning? Dynamical systems arises because learning algorithms can be thought of as dynamical systems. So if you have some data and we learn these models through optimization algorithms, and we're going to look at these optimization algorithms as dynamical systems. So that's where the dynamical systems angle comes in. And traditionally in the field of learning theory or statistical machine learning, which is a popular theoretical area within computer science, this learning algorithm is really treated as a black box. That you just think of the learning algorithm as taking some data and giving you some output, which is the learned model. And then no matter how it behaves, we just think of very general bounds for how well the learning happens. So this work is about opening up this black box of the learning algorithm and seeing what are the many ways in which dynamical systems can help complete this picture of generalization. I hope at least a little bit of what I said makes sense. And before I proceed, I'll say that the first part of the talk, which is going to be about generalization, and I hope Yeah, I hope you can see my cursor more, is joint work with Andreas Kasher and Stephanie at MIT. And then I will take a small detour to explain some implications of this for scientific machine learning in general. And that is joint work with Chi. And then the second part on learning chaotic dynamical systems, which are a class of nonlinear systems. That is joint work with my student, JJ. So let's, with this introduction. So I don't have to go through everything. Since I understand this is a class and it can be quite interactive, and you can stop me and make me just explain something which may not be new research, but rather, hopefully whatever I'm saying is useful to some aspect of your research. So that's the goal. So if you would like to stop me at any point, feel free. I don't have to complete the material like a regular research talk. So as I said, the object, the point of these studies is to understand generalization, right? And the dynamical systems point of view is relevant to mainly consider learning algorithms, both discrete as discrete time dynamical systems. And these learning algorithms are typically deterministic, like gradient descent. There are a class of deterministic algorithms, full batch algorithms based on low-code descent. Then many batch algorithms and several other variants like stochastic gradient descent and its variants are stochastic algorithms. But you can think of both as discrete time dynamical systems, either deterministic or stochastic, but they are Markov processes. That means that their state at the current time only depends on their state at the previous time, or at least the probability of being at a particular state at the current time depends only on the state at the previous time. And as opposed to other areas of numerical, say, mathematics, where we study, say, algorithms as dynamical systems, and we are interested in, say, an ODE or a ODE representation, ordinary differential equation representation of the system, there the questions that are asked are different. Whereas the dynamical systems theory point of view is really to say what happens to all possible orbits of the system. And by taking the dynamical systems perspective, we mean that we want to use information about the stability of orbits. These are usually called stable, unstable manifolds of the system. And we want to use information about them to understand how the stable and unstable manifolds that characterize the dynamics of the optimization algorithm, how does that help in understanding generalization? Potentially, this studying the nonlinear dynamics of algorithms can help us to exploit the fact that exploit more of exploration done by the algorithm and say something like we can learn the same model or a model that generalizes in a similar way, but with much fewer number of parameters. This can be a potentially very big consequence of looking at this perspective. And secondly, which is just a theoretically interesting, probably the greatest theoretically interesting question in statistical machine learning, which is what are these different pieces that contribute to this overall picture of generalization, right? How does, if you have some data, what can you say in very complicated settings about how well we are going to perform on data that is not seen during training? So I've already said what this is. So I will talk about two things. Generalization, which is generalization of a learning algorithm. So here you can think the object that we want to learn is just a function. So if you have some pairs x, f of x, we want to learn some f that can give accurate values of the true function f of x at a different x that is not in the training set. I would just like to point out that dynamical systems theory can also intersect heavily with this area of sampling, which is a problem of getting or generating samples from an unknown probability distribution. But I will not be discussing this here, although there are many intersections of dynamics with sampling algorithms as well. But I will be discussing in the last part the generalization of forecasting, right? Here we are not just interested in learning a function, but we are interested in learning a time series. So in particular, we'll be looking at learning time series data, which are chaotic orbits. So in the first half of the talk, the key takeaway is that if you look at a learning algorithm, the more stable it is in its long term, and I will define what long-term stability means, the better it generalizes. This is the main message. So to understand this message, let's start with the motivation for studying optimization algorithms as dynamical systems. So let's just assume that we all have some neural network that we are training. And then typically what we do if we stop the optimization problem at some point when we are satisfied with the training error and the test error. So test error is just the error that we evaluate on points that are not used in training, but from the same data distribution. But this is a bit of an exaggerated case which may happen in practice from this paper, where beyond the stopping point, if we were learning something like a function, maybe we would stop here at 50,000 time steps because we are satisfied with the error and the test accuracy. We're satisfied with the test accuracy at 50,000. We're satisfied with the training loss, but then it keeps oscillating forever. Like especially these stochastic algorithms, there is it is not that meaningful to consider them as converging to a particular fixed point. And there's been a lot of recent interest generated in understanding how these fluctuations about a fixed point in the parameter space of optimization contributes to generalization. And there are several works in this direction, but I'd just like to reiterate the point that even in a simple setting, where if you take a one-dimensional optimization problem and the objective function is non-convex, then you will see that either you have some fixed points and there will be some oscillation among those fixed points. And as you increase, so the x-axis here is the learning rate. And as you increase the learning rate of these optimization problems, you could even get other kinds of behavior, periodic behavior, even chaotic behavior, right? But there has been recently many works that have studied how these fluctuations, which many people have observed is actually heavy-tailed, how the heavy-tailedness of these fluctuations affects generalization performance. So the upshot is that we are interested in studying an optimization algorithm that may or may not converge to a particular point in parameter space. And in this setting, how can we define the generalization properties of these algorithms? And secondly, can we look at the training algorithm as a dynamical system and then understand how to predict its generalization performance? by looking at its dynamics.
So what do you mean for generalization?
Yeah, maybe I can define it in the next slide.
Oh, okay, thank you.
So let's define the problem. This is an optimization algorithm, which is just a version of local descent. So WT are weights and biases, so parameters of a neural network at time t. And eta is the learning rate. And let's say you have some set of samples S, which contains n training examples, Z1 through Zn, each of which is independent, identical, distributed according to some D. And you can define a loss function, which is called the training loss, which is simply an average of some loss objective little l. The first argument is Z, the input. The second argument is W, the parameter in space. Okay. So if we are doing gradient descent, then we take the gradient of the training loss at some WT. We are doing stochastic gradient descent, then we approximate the gradient on the training sample using a smaller batch of samples. So both of them take this form. This is the update, and this is the dynamics we are interested in. And if we just look at it as a nonlinear dynamical system on parameter space, so you give it a WT and you get a WT plus 1. It's doing some dynamics on this high dimensional space of weights and biases of a neural network, right? Now, this system is in general a nonlinear system, and we can exclude cases where it blows up or some pathological cases. So you can think of this as it is in some bounded set in a high dimensional space. And in this setting, anything can happen. It may converge to a fixed point. It may not converge to a fixed point, but keep oscillating indefinitely, so on. So we don't make any assumptions on the asymptotic behavior of what are called orbits. When I say the word orbits, what it means is you take some W0 and you repeatedly do the algorithm. The sequence of WTs that you generate is called an orbit of a dynamical system. Okay. But what we know from ergodic theory, which is essentially the study of the statistical behavior of all possible orbits of a system, is that there could be multiple different ergodic distributions on the space M. Now, remember that this M is the phase space of this dynamical system, that is the space where all the weights and biases live. Now, let me explain what, yeah?
One question. The learning rate, is it fixed?
Yes.
Or that's what I thought. So you don't really change the learning rate or the step size to try to minimize the function.
Yes.
I get it, yeah.
Yeah, so
That's why you get the orbits.
yes, so I have not done this analysis for adaptive learning rates.
Right.
Just to keep the setting really simple,
Yeah.
we've just considered constant learning rates.
Nice.
So probably, yeah, you should definitely have some pizza if you're all hungry.
That's okay.
But yes, so let's look at the probability. Let me define what ergodic means, okay? Since this talk is only an hour, I'm not gonna go into details, but let's just understand that if we have an ergodic system and there is some measure or probability distribution, mu, on this phase space, what it means is that if you take the time average of some functions f along orbits of the system, so f can be any function that maps from m to a scalar, and if you take a time average of that function along an orbit, as time t tends to infinity, or if you take an infinitely long orbit and take its time average, it is the same as taking an expectation with respect to this measure mu of the function f. Okay. So there is a probability distribution on phase space which describes time averages, or which describes the behavior of all possible orbits as a spatial average. That's what ergodicity means. It means that the initial condition is forgotten. So this holds for all initial conditions. You can just ignore this mu almost everywhere if you've not heard of this or seen this notation. You can just think that for any W0, as you take the time average, it converges. So all possible orbits give the same time average, and that constant is this expectation. But when we are training deep neural networks, right, there could be many such distributions mu. That means that if you start from some W0, you get a time average, it converges, but it converges to a different expectation or expectation with respect to a different measure than another W0.
But this means because state space, it is multiple regions that are independent, they are disconnected.
They may not be disconnected, the supports of these distributions, but it is a very complex setting. So we cannot assume that there is a unique mu. So just pictorially, this is what this is showing. The axis numbers are not important, so you don't really have to squint to read them. What is important here, what is plotted is 4 different orbits of optimization of a deep neural network training, which is in high dimensions, but it is projected on 2D using a dimension reduction algorithm called TSNE. Now, each of these orbits are settling in different parts of the phase space. And if you take the color just represents the epochs or the time. So it's saying that, this orbit goes over here as time increases, this orbit goes over here, this goes over here, that goes over there. And they all have 4 different initial conditions, okay? So depending on the initial condition, it could actually do different orbits, explore different parts of the weight space. Right? But then we make a reasonable assumption, which is that if you take the time average of a loss function for any input z, if you take the average of a loss function, let's say like a mean square loss, any loss function, then that converges, the time average converges to a quantity that is independent of the initial condition. Okay. And this is reasonable because if you think that, you and I are training neural networks, we have the same data set. When we train them, we are going to start with random initial conditions. We're never going to have exactly the same initial condition. But then we have these standard benchmarks that say, okay, the test accuracy is almost the same. If the architecture is fixed, the training data is fixed, the training accuracy, the test accuracy are all similar, but venus. Right? So we think that, and that's plotted here for different architectures. You can see that the training time average, the test time average of the training errors and the test errors, those converge no matter the initial condition to reasonably the same values. So this is the assumption. And remember this, it will keep appearing. This is the time average over an infinitely long orbit called an ergodic average. Or equivalently, this is some constant, which is an expectation with respect to any of these ergodic measures, but it gives the same constant. And it is only a function of the parameters of the system. In this case, just the training set. Let's assume every other parameter is fixed, like the learning rate and other bells and whistles that you have are fixed. So I'm only writing this as an average with the subscript of S and this loss function at the input Z. So there's a class of different loss functions parameterized by this S. Okay. Now, what happens is that if we make this assumption, we can kind of extend somewhat standard machinery in the case of in the world of statistical learning, which assume, which can be used to prove generalization bounds, we can extend them to settings where the algorithms that don't converge. And let me explain what the standard thing is, and then I'll explain what we are doing new. So this is a notion called algorithmic stability, which basically tells you that an algorithm, a learning algorithm, is beta algorithmically stable. But beta measures the robustness of the loss function to changes in the set, training set S. Remember that this S was the training set consisting of n examples. Here S prime is the same as S except at one point. So you have your training set, you take out one example and put a different example from the same distribution. Then this is the value of the loss function that you get at loss function at this input Z, and WS star, where WS star is the parameter that you obtain when you train this optimization, when you perform optimization with the set S. And similarly, WS prime star is the value of the parameter you get if you train with S prime. Now, this thing measures how robust is your loss function to a small change in one example in your training set. Of course, the problem with this is that in modern machine learning algorithms, we don't really have this one point in parameter space where we converge to. So we can replace this notion with a statistical notion of algorithmic stability and say that we can say an algorithm is statistically algorithmically stable, or say SAS, with a coefficient beta, where beta measures the maximum amount of discrepancy in the loss averages if you train with S and S prime. Is it clear? Yeah. So just like the classical notion, if the value of beta is higher, that means that your loss values are more sensitive to a small change in the input. So it is less stable. This kind of thing applies both here and here. Now, now we are saying if the loss time averages are less stable, that means you have higher value of beta.
So beta, it is like a standard deviation, like a large the theory of large numbers in.
Not really.
Not really.
So the beta is just defined exactly like this.
Okay.
The supremum over all inputs, the supremum over all possible sets, S and S prime that differ by one element from the same distribution of this thing, which is just the scalar difference.
But you could also define the same thing for S's that differ by more than just one, correct?
That is.
But you really like just the jackknife kind of a definition.
Yes,
Yeah, okay.
exactly. And there's a reason for it. The classical proofs of generalization bounds, which I'm going to show you, consider one sample perturbations. This kind of a leave one out setting is very common in statistical. So this, but unlike this classical notion of algorithmic stability, the statistical algorithmic stability applies to non-converging algorithms now, because we have not really assumed that the algorithm converges, right? And so it is just a more general thing which doesn't depend on any particular point in the phase space. So here are some just visualizations of what beta looks like when we train a deep neural network. So here are just the standard convolutional neural network called VGG16 and a standard data set of images called CFAR10. Okay. Now, I'm going to show you 5 different models. These are actually the same neural network, but the data set, the true data that you're trying to learn, or equally the true function you're trying to learn, is different between these 5. And how is it different? Well, the original CFAR10 data set and the original function is always shown in black, right? And these other colors represent noisy versions of this function. So for instance, this blue one is the same data set with a probability 0.1 of having a random label. The red one, for instance, has a random label 50% of the time. That means the function that you're trying to learn is almost a noise. It's noise 50% of the time, and 50% of the time there is some real life meaning that is ascribed in this true function in the CFAR10 data set. Okay.
And how do you introduce this randomness? Every other point or just randomly, you just take
right, for any data point, I would, with probability 0.5, assign it a random label.
So for every point?
For every point.
Okay.
So now what is shown here is a calculation of the time averages of training with some set S prime and some set S, and we take the difference, right? So this is a way of estimating beta numerically. Of course, if you look at the definition of beta, we are taking a supremum over all possible sets, supremum over all possible inputs. It's not possible to actually compute it. But if we approximate it over a finite number of pairs, S and S prime, we will get a lower bound on beta. Okay. So you should interpret this as a lower bound on beta, which is plotted here. This is on the x-axis is the percentage of corruption. And you can see that roughly, as you increase the percentage of corruption, the lower bound on beta also increases. Okay. It is suggesting that when the true function you are trying to learn is more and more noisy, then the algorithm is also less and less statistically algorithmically stable. Because higher the value of beta, less stable the algorithm. And we also know from our intuition that if you are trying to learn a function that is noisy, it will generalize worse because we will just overfit. While training, we will just overfit to the noise. So if we give a new point, it's not going to really predict as good as a random guess. So that means it doesn't generalize well, right? So this is what we observe in practice is that when we increase the percentage of noise, the generalization error, which is approximated with the test error here, also increases. So it seems like there's a connection between beta and the generalization error. And in fact, there is, and we can prove that greater the beta, greater is the generalization gap or worse is the generalization performance. So in order to prove this, we will also define a version of training and test error that is independent of a point in phase space. And so that it applies to algorithms that actually don't even converge to a particular point. So here is the training error, which is defined in the usual way, except that the loss is now replaced with the average of the loss. And here is the generalization error, again defined in the usual way as the expectation over all inputs of instead of the loss at a particular point in phase space, now it is replaced with the average of the loss over the phase space. Phase space is just the space of weights and biases. How am I doing on time?
It's good, it's good.
You're doing well.
You're doing well.
Okay, really? Okay. So I think maybe I'll get through half of the talk because I just want to go slowly because
We have time
it's
until 2.
a new thing for.
So we will,
Yeah. So really what the theorem says is that, so the theorem basically informally means that statistical algorithmic stability implies generalization. That means that if you have that is saying that this gap between the generalization error and the training error, this is usually the holy grail object in all of statistical learning, is to try to bound this gap. So if the training error is almost zero, so you train the algorithm so the training error goes to zero, the generalization gap is the same as generalization error. In that case, how big is that? That is the object we typically try to bound. And here it's saying that that object is on the order of beta times square root of n, where beta is the statistical algorithmic stability coefficient of the algorithm, which is saying that higher the value of beta, the worse your gap will be. Or in other words, smaller the value of beta, better is the generalization.
So Nisha, can I ask one more fundamental question? This loss function and the difference you are using there is about the errors along the orbits, the final orbits. But the objective of the whole thing is really to see if we can, if the algorithm can identify the function itself.
Yes.
It's not so much the errors. So do you have a measure that actually says, even if I have a 50% probability random error in there, that you can actually get close to the function you're trying to compute?
That's actually a really good question. So typically in machine learning, this is what they want to, this is the object. The loss function is what they want to minimize. Whereas maybe in science, we are more interested in pinning down the function.
For us, we will find the function,
right?
no matter
Because
if it's corrupted with error.
Yeah, because typically for many different functions, you get the same loss because there are some symmetries and there are many possible representations of the same function, because even in the neural network, there are various symmetries. But you are absolutely right that there should be some notion of generalization that is particular to a problem in physics or whatever you're studying, right?
I say that because no matter if you have a high B and the system is unstable, or at least the algorithm is unstable, I have seen that because we've done some experiments like this. And even if you have corruption by noise and you increase the standard deviation of the error, you still can actually get to the function because of the averaging. You know what I'm saying? So, which means that we can still get a good result out of an algorithm like this, no matter if the loss function shows a gap and a high difference between the RS and the RS hat.
I see. Yeah, you're right. So if you're learning the true function, then the loss function is a good representation of learning. But sometimes you might be learning the true function, but the loss function is not really indicating whether you're learning that function. So that probably just means maybe you can redefine the loss as, say, instead of looking at the average, you can look at the loss at a particular point. So you can always redefine the loss in such a way that it is applicable to, it is more an accurate representation of
you
your
can do that here in this experiment you have here, because you are the one who created the function in a way, and then you perturbed it by errors. You can define that because you have the true function, right? So you could actually, in parallel to what you do here, you can also check to see how close for different betas and different corruption of random noise, you come to the function itself, so that you can see the difference and what makes sense for some of our.
Right, that's a good point. Like for this particular example, I really think that the functions that are being learned are going to be different for different, because for instance, you can fit the same data. The CFAR10 is actually just a collection of images which have 10 different classes, right? You can train several different convolutional neural networks that all can classify really well this data set, right? I've used VG16, you can use a ResNet, a residual net architecture, you can use similar architecture. Then they're all different functions, different classifiers, right? But they can all do a good job. There are many different functions, that can produce a small value of the loss. It's kind of a different thing than, maybe the second part of the talk is related to what you're asking, because the second part of the talk, we want to learn a physical model. Given a dynamical system, we want to learn its model.
Maybe can you go there now?
Oh, sure.
No, it's okay, it's okay. You just do what you want.
Yeah. I mean, no, if you already have, that would be interesting,
Yeah, so, okay, this
Yes,
is,
that's of interest.
this is probably, I have another result relating generalization, but maybe I will skip this for the second part, which is about learning chaotic dynamical systems. I'll hide this actually. Chaotic dynamical systems from data. Okay, so here I'm trying to learn a particular. You can think of chaotic systems as arising in general in many settings, right? I'm sure you all encountered turbulent flows in fluid mechanics, or it could be something simple from ecology, or it could be planetary motions. It could be many chaotic dynamical systems in nature. And we want to ask the question of, can we learn it? Can we learn the true governing equation of these chaotic systems purely from data? Okay. And the data we have are just time series. So let's say you're observing a bunch of planets that are executing chaotic dynamics. Then you have the positions and velocities of the planets at one time, and then the next time, and the next time, and so on. So you have an orbit of this dynamical system. And from this orbit, you want to learn the equations. Now, this is a very popular setting in scientific machine learning. And one way to do this is through this type of learning algorithm called neural ODEs. Okay. This is a framework where the ordinary differential equation on the right-hand side is represented by a neural network. So here H is the right-hand side. So this is actually an ordinary differential equation, but many of you may not be familiar with this notation. Let me explain what that means. So we usually write dx dt equals h of x, xt, right? But really you should think of this as an orbit starting from some point x in Rd. X is the initial condition. Pt means where is the x after time t. So Pt of x is where the dynamics is at after time t. And the subscript just indicates what is the driving force or the right-hand side, h. Okay. So Pt h of x is simply the state of the dynamics starting from x after time t, with the right-hand side being the function h. The function h is a function from Rd to Rd. So Pt h of x is always in Rd. It's a vector in Rd. Okay. So with this notation, h here is a neural network. In a neural ODE, the point is to learn h just from data. What kind of data? As I said, you have orbits of the dynamics. So you can really think of this, even though it's a continuous system, you can continuous in time system, you can think of it as a discrete time system, because what you have in practice are, say, observations of x, the state, after time delta t. So this x is the true orbit of the system. So say you start at a true point x0, x delta t is the state after time delta t. And you're trying to fit it with, by solving this neural network ODE or neural ODE at the same time delta t. Okay? So if you minimize this error, this is now your optimization problem. This is a loss function, right? That takes an input, and this is the network function h, and this is a loss function. If you minimize this, it really, actually you already preempted what I'm going to say from here on, which is that, okay, this is how it is done in practice, is we try to minimize this loss function. You preempted the next part of the talk by asking, does this mean we are actually learning the dynamics if we minimize this loss? And that's what we are asking, okay? So first, let me just belabor the point by saying that, okay, in neural ODEs, we will take this as a loss function, then we calculate the training error, the test error, the standard way, right? Just as we've done in the first part of the talk. Now our sample data are coming from a dynamical system, and our loss function is defined in this way. We are going to do some optimization for the parameters of H. So H is the neural network. So the parameters of H are the W's. We will do an optimization algorithm for that. We get the training errors, test errors. And the test errors can be made very small. Okay. So we will conclude, if we were in a computer science setting, we can conclude that the algorithm generalizes well because the test error is small. Okay. And that's what I'm showing you here. These are plots of the training loss and the test loss done by JJ, where you have, she's trained it for a long time, and you can see both of them are kind of decreasing and the values are small, good enough for us to call it a day, right? And the underlying model for this is called the Lorentz 63 system. I don't know if you have seen this, but it is a classic example of a chaotic system. I'm just going to show you. If you have not seen this before, actually, it is very likely you have seen it somewhere in a movie or something because it's very popular, right? It was the first example that was suggesting that the Earth's climate system would be chaotic. It's a 3-dimensional system, which is supposed to be a reduced order model for convection in the atmosphere. Okay. And what I'm going to show you, so it is a 3-dimensional nonlinear system, nonlinear ODE. What I'm about to show you is what it means for it to be chaotic. So the word chaotic has a very precise mathematical meaning. It means that an infinitesimal perturbation blows up or increases in norm exponentially in time along orbits. And to see this visually, we look at the trajectories or the orbits of the Lorentz system, all starting in the center of this page over here. You have several different initial conditions that are all very close. Okay, so you can just see it as one point. Each initial condition will have a different color, and I'm just going to solve the 3 ODEs in time. Okay, and this is what happens. Initially, they were all together, and now you can see the colors are kind of slowly moving away, and over time, yeah, over time, and you've all seen this. I've just forwarded a little bit into this same video. Now the initial conditions have really spread and settled on this butterfly-like structure, which is called the attractor. The attractor of a dynamical system is where all the orbits eventually settle down. And after even longer time, you just look at it and it looks white, right? It means that the colors have mixed. That, in other words, the probability distribution on this attractor has converged. Okay. So when we say we want to learn the dynamical system, what we really want is to learn this probability distribution. Because when you saw the initial part of the video, each orbit can execute completely uncorrelated dynamics, and a small perturbation can lead it to a different orbit which is so uncorrelated, which becomes exponentially uncorrelated from the original one. So in our setting, if we are trying to learn the dynamics by mimicking one orbit of the system, it does not mean that we are actually learning this dynamicals. It's intuitively very clear. How do we analyze this and how do we remedy this problem? So the Lorentz 63 system is an example of an ergodic chaotic system. Ergodicity means exactly what I showed you and what I discussed before, that time averages converge to expectations with respect to omega. And in the case of Lorentz 63 system, and in many other examples that are interesting in various areas of science and engineering, we have this probability distribution called a physical distribution, which describes all orbits. As I said, if you start from any random initial condition and time averages converge to expectations with respect to this measure, it's called a physical measure. And this physical measure is the strange object for the Lorentz 63 system. It's supported on this butterfly structure, and it is a singular measure. That means, if you know what that means, it's not absolutely continuous with respect to volume, but it's okay if you're not familiar with that. It doesn't affect the rest of the talk. And another concept I want to introduce is the concept of Lyapunov exponents. A chaotic system, one definition of a chaotic system is that it has at least one positive Lyapunov exponent. A Lyapunov exponent, if you've studied this in a nonlinear dynamics class, it measures how fast an infinitesimal perturbation applied to the state of a system will increase or decrease in norm along the orbit. So this is a part of what's called linear stability analysis in a general nonlinear system. And chaotic systems are unstable in the sense that they have at least one positive Lyapunov exponent. At any point in their orbit, if you make an infinitesimal perturbation, it is going to grow under the linearization of the dynamics. So, and these Lyapunov exponents, they are defined analogously to eigenvalues actually, except that the matrices are now changing. They are Jacobian matrices along orbits. And they are ergodic averages. That means they are constants of initial condition. So these are the true Lyapunov exponents. It's a 3-variable system. It has 3 Lyapunov exponents. The first one is, of course, positive because it's a chaotic system. And we see that when we train a neural ODE that generalizes well according to our defined loss function as the mean square loss, we see that somehow it gets the first exponent right, but then the last exponent is just wrong. So this is the true, it's the same attractor that you saw before on the top row. This is the true attractor from a numerical simulation of the 3 ODEs, just projected on the X, Y, X, Z, and Y, Z planes. And here is what an orbit of a neural ODE starting from an initial condition, just a different, after training, if you start from a random initial condition and ask it to do, just use the neural network to solve the ODE, you get an orbit that looks very different from this butterfly.
Did you train with data from the attractor? So if you start off the attractor, does it know any dynamics really?
That's very interesting. So the same trend is observed whether or not your training data starts on the attractor or off the attractor. And no matter how long your training data is, how many samples you use.
Because the orbit goes, for this particular system, the orbit goes very quickly to the butterfly shape.
Yeah.
Yeah, so that's why it's the same. If it was a longer lag time to go
That's
from there,
true.
then it would be a little different.
Oh, yeah, you're right. Yeah, I think it would make a difference if the transition times were very long, and one can think about, oh, maybe it's not learning the dynamics of the attractor or on the attractor. But here, because as you said, the transition time is short, it is not the lack of learning dynamics of the attractor that is causing this lack of ergodicity in the neural ODE solution.
Do the neural network converge to fixed points?
The neural network, does converge in that the training loss and the test loss are small. They fluctuate about a very
No, I
small.
mean, when you apply the neural network, with
But
an initial
this
condition.
converge to, so sometimes it converges to a fixed point, sometimes it shows some periodicity, sometimes it goes to-
The neural network has positive Lyapunov exponent, so it is chaotic, is right?
Right, some
But it's actually
orbits,
showing some orbits.
some orbits are chaotic, and it could also be, even if it converges to a fixed point, the fixed point could be an unstable fixed point. Just because you have a positive Lyapunov exponent, it doesn't mean that it has to, it reproduces exactly this attractor.
No, I mean, yeah, I understand, but now this one, what is the attractor of the neural attractor? What is the attractor of?
See, so in this case, I believe the attractor that is plotted does go to a fixed point because the colors actually indicate the time and the colors concentrate, the pink one concentrates over here.
Yeah.
So I believe it's achieving some fixed point.
And the other two realization is the same?
Yeah, it's the same realization that is projected on 3 different planes.
Oh, okay, so it's going to, there is a stable fixed
Yes.
point, there is
Unstable fixed point.
if it's unstable, it will never reach
It will
there,
never
right?
reach there, right? So I think it's just constantly oscillating. It never actually
Okay, okay.
reaches there.
So maybe if you zoom inside there, I wonder how it looks, because no, maybe not, if you zoom inside inside there, no? In the little dot, maybe the dynamics there is gonna look chaotic. There will be some,
Right.
So I think, Nisha, that what happens is, if you try different neural network architectures, you can replicate a chaotic orbit. Sometimes it will be fixed points that the thing converges to. I have done this actually.
and not necessarily it's a fixed.
So it depends on the structure of the neural network you're using to be able to replicate the chaotic dynamics or to make it go fixed. So if the network is not actually is more simplified, it's going to converge to a fixed point. If the network has many more parameters, if you do that with a few layers and so on, then you're going to replicate what the Lorentz attractor is. That's what happens, yeah. So it depends. It's also a matter of the architecture you're using to see how close to those Lyapunov exponents you can get.
Exactly,
Yeah.
exactly.
Yeah.
So
It's another.
yeah, so definitely there are 2 reasons. So the point of this project is to study the generalization ability of a model for the chaotic system that generalizes well according to a simplistic definition of mimicking orbits. So if you have, so this is maybe the simplest possible neural network. So basically we chose a 3-layer, as you said, if you make it more expressive, we can learn chaotic orbits. But with just this, it's able to reduce the generalization to a very small value. The error is so small, and yet it is not reproducing the dynamics.
Because that's the average. You're using the average of the orbits as the.
No. Oh, yeah, okay,
You see?
because it's a mean
So
square
the
error.
average- Yeah, the average can be very close, actually identical, but the in between orbit can be quite different from what the actual system does.
Right,
Yeah.
because the errors are actually, so with, if we look at this, we look at the errors. So this is the sum of 10,000 values, and it is very small, right? 5 times 10 to the minus 4. So at each of those 10,000 points, it is quite close because it's a sum of like 10,000 positive numbers. So it is learning the system, or it's learning the training data well, but not the statistics. So, yeah, that's exactly right. How am I doing on?
You still have time, you're good.
We still get pizza.
Yeah, we still have pizza, so until 2 p.m. we're good.
Yeah.
If you want, you know, you can, if you want to continue,
You have to get some pizza.
Love to talk more. So, and this is also a very interesting discussion. So, we have to ask ourselves, so when we define generalization, a good generalization doesn't mean actually learning the dynamics in this setting. So it makes sense to redefine generalization to, to distinguish a model like this, which I just showed you, which was not learning the dynamics, to say that that generalizes poorly, rather than just looking at the typical way of defining generalization. But to understand that, to how do you get there, how do you redefine generalization, we can be guided by dynamical systems theory. So this is another example of where dynamical systems can intersect with statistical learning. So clearly the loss function, right, is small at almost every x. That means that the true orbit is close to the generated orbit at these points. Right? However, the statistics, so we now start from a random initial condition, you calculate time averages of these neural network orbits. They may not be expectations with respect to the probability distribution that we saw on the attractor. So you can really think of this neural network as what is called an epsilon perturbed orbit of the original system. That is, at each point x0, the output of the true orbit and the output of the neural network are epsilon close for some small epsilon. Okay. And the theory of dynamical, some types of chaotic dynamical systems, here I'm just going to be very informal. It states that if you have an epsilon orbit, that is, if you have two models that are very close to each other at every point, then a perturbed model has some orbit of the true model that will closely follow it. Now, it can closely follow for infinite time in some really ideal scenarios called uniformly hyperbolic systems. I don't want to go into the details. But usually it is for a finite time. There is a finite time shadowing. And this is in all of numerical methods for chaotic systems. We take this as a justification for why we are simulating the true physics. Right? So let's say the true physics is something that satisfies the true governing equations that we have written down. Let's not debate whether any model is perfect or let's just say that's the true governing equation. And the true orbits are some things that satisfy this governing equation. Now, whenever we do a numerical simulation, we're going to approximate it. When we are on a computer, we approximate orbits, right? But because approximate orbits are epsilon orbits, at each point they are close to what the true orbits will do, because numerical time integrators have a small error at every time step. So at every time step, if you take some x0, you do the true ODE for a small time step, and you do a numerical solver for a small time step, the results are epsilon close. So that means that this epsilon orbit, which is a numerical simulation, is closely followed by a true orbit. And therefore, we are satisfied that yes, it is simulating a true orbit of the, so it satisfies the governing laws approximately, right? And this is generally thought of as the justification for, the shadowing is used as a justification for numerical simulations of chaotic systems. Because in chaotic systems, otherwise we have no way of concluding, because they're so sensitive to initial conditions and small perturbations. How do we know that what we are generating on a computer really satisfies the true governing physics? This is used as a justification. Yeah. And let me also show you in an example. So let's say we have a one-dimensional chaotic system. So it is this is the interval 0 to 2. And this is a discrete time dynamical system or a map, which simply maps the interval to itself. This is that function. Okay. And the dynamical system here is just repeated iterations of the same function. So if you take a point here, it goes here. Then you take 0.5, it goes to 1.5. Then you take 1.5, it goes to 1, and so on, like this. Okay. this is the orbit and it is a chaotic system. I will already tell you. Now this value of S, it indicates 4 different models actually, but they look identical. You only see the last one here because the perturbation is so small. Okay? The perturbations of S cause a very small epsilon perturbation to the map. On the right-hand side, you see the physical distribution associated with S equal to 0 is shown here in red, and that is uniform distribution. Okay, just take it from me. It's easy to calculate that it is a uniform distribution. Now, this blue thing is an empirical distribution taken from a long orbit of a shadowing orbit. So the blue is an empirical distribution of an orbit that does satisfy the true equations of S equals to 0 map, okay? And yet, it does not follow what any other point, any random point does, which is finds a uniform distribution. In other words, shadowing orbits can be atypical. So there are true orbits of the system that can give you atypical statistics. You will not encounter them, but they exist. You will not encounter them because if you start from a random initial condition, you will observe what is physical. But there are things that are not physical that also satisfy those equations. Like one example my advisor likes to give is there are some laminar flows which could be unstable unstable orbits, laminar solutions that could be unstable, but satisfy the same equations as a turbulent flow, which is what we will observe, because when we do any simulation, you'll get perturbed because it's unstable and it'll give you a turbulent solution. But those solutions exist, and shadowing orbits could be unphysical, atypical.
And the probability of those unstable orbits?
Very good question. So we studied this. It's very difficult to give a general result for the probability of finding unstable orbits. For specific systems, we can show that there are, like for this system, with like 99.99% probability, they will be unphysical.
You know what I'm saying is that the probability of occurrence of those unstable orbits is critical, because if the probability of them occurring is just very, very small and tiny, that's why you don't observe them, because the physical system.
Oh, that is 0 actually. Yeah. The probability of atypical orbits is 0.
Always small, then you get to 0. Yeah.
It is 0. So because we calculated in terms of Lebesgue measure. Yeah. And these are Lebesgue measure 0 points. For instance, if you take the interval 0 to 1, that has Lebesgue measure 1, uniform measure 1. Lebesgue measure on this interval is just a uniform distribution as 1, right? And you can encounter rational numbers. Any number that you can represent on a computer is a rational number, right? Rational numbers all rational numbers on 0 to 1 together have a measure 0 on the space of 0 to 1, right? But then any orbit that you can represent on a computer is a rational number. So they are all atypical for a system for which rational points are atypical. So it is, but if you theoretically, in principle, if you take a random point on the interval 0 to 1, it will be rational, because the probability of getting a rational number, all possible rational numbers have together a set of measure 0. So it is, the shadowing orbits can be atypical, and this kind of has implications. This was a little segue that I should really not be going into right now, so I'll just stick to the point, which is that sometimes with statistical learning theory, you can prove that this generalization error can be made as small as possible when you increase the length of the orbit of training. However, because shadowing orbits are atypical, it does a very good job, the neural network does a good job of learning a shadowing orbit, but the shadowing orbit may not be typical. So this is one reason why neural ODE may not generalize. And what we found is that for the same thing which generalizes well, the same system, if we add a term to the loss function, which now matches not just what it is after delta t, but also matches the Jacobian of the function, now we are able to reproduce the model itself has not changed, but the loss function has changed. Okay? So this actually has a deeper reason why it is working, because, and I don't have the time to go into this, but essentially it is learning this thing called the measure theoretic entropy of the probability measure. And therefore you get, now you see these are randomly chosen orbits in the bottom row generated by a neural network, and these are generated by a numerical simulation, and it does well. You can calculate all kinds of correlations, statistics, everything matches reasonably well. So we want to ask this general question of why does this work? Is there any other thing that you can add to the loss function that can reproduce the statistics of the system? How do you use both shadowing theory along with statistical learning theory to get improved bounds for learning chaotic systems? And there's a general message here. Now, if you have a physical, I've shown you this with learning chaotic systems, but if you give me a setting where you're trying to learn some particular system, how do you combine, how do you redefine generalization that is specific to your setting? For example, you might not care about reproducing orbits of the system, but you care about, say, you're a control theorist who cares about solutions to some constrained optimization problem. So we can define generalization errors such that that solution to the optimization problem is mimicked rather than the orbits of the system, because that is what that is the use case for that system. So in general, the theme is to define generalization errors based on the what you're trying to learn rather than the way it is done in, say, image classification. And the overall more general theme is that there are many interesting problems at the intersection of dynamics and statistical machine learning. And we can discuss more if you are interested in this field.
Yeah.
Thank you.
Thank you. Can you please stop the recording?
So Nisha, the application of this